So as promised last time, what we're going to do next is look at a full vibrational analysis of a molecule. Now what you'll find is this is essentially the same type of thing that we did for the stretch only analysis. The difference being that we're actually going to consider all different types of deformations that may be or may not be, depending on the symmetry, infrared or Raman active. So, what are we talking about for that? Well, we do have the stretchings that we saw before, which are usually the strongest. There are also things called wags, bends, and there's various other deformations. Where these typically will show up is in that area you may remember from taking IRs in organic lab, the fingerprint region. They're generally lower energy, they're not as distinctive, but they can give you a wealth of structural information. And what you can actually do beyond what we're doing here is step into a normal coordinate analysis where you can find every possible deformation of every bond in a molecule, predict their energies, and then take the spectra and do all that. But again, that's a computational thing that can be done. So what is the difference between what we do for a stretch only versus a full vibrational analysis? Well, actually what we're going to do is we're going to add something in, right? Because three-dimensional molecules have three dimensions. They have 3n minus 6 degrees of freedom. So if that's the case, then any of those degrees of freedom will give you some type of energy. So what we're talking about here is we're going to add in not just vibrations, but also rotations and translations. Once we do that, we analyze the data that we have, then we take that information back out. We take away the information about the translations and the rotations, and you're left with the vibrations. So again, that's all just sort of background information for what we're going to do. What you'll need to be able to do is actually do this. So let's look at that. And this time, since we're looking at these lower energy type of things, we're not going to look at carbonyl stretches or cyanide stretches or something like that, because those are really strong, high energy things. Let's instead consider this molecule here. Cyclobutane, C4H8. There's a few things we can say about this. The first one is there's been controversy about what the geometry of this thing would be. It could be square. It could be rectangular, where these two bonds, let's say, are longer than those two bonds. Or you could have a twist in it, a puckering, which would then render the symmetry much lower. And so, believe me, you could do a full vibrational analysis for all three of those. And if you had the spectral data to compare it to, you could figure out which one it is. We're not going to go through all that. We're just going to take one of the three, and we'll pick not the easiest, but the most illustrative one. And that is if this was actually a perfect square. So once we have that, what we've got to do is analyze it for which point group it belongs to. So again, we've been through quite a bit of this already, but let's look at it again, since it's useful. At the center of this molecule, we're going to have a C4 axis of rotation. There's also a collinear C2. That is doing the C4 twice in progression, but it is a unique symmetry element. Do we have n perpendicular C2 axes? Yep, we do. 1, 2, 3, 4. Two of them contain atoms in the molecule, two of them don't. And so you can guess what's going to happen with the planes that are going to come out of this. Do we have a horizontal mirror plane? Yep, we do. It's in the plane of the board. Alright, so if the principal axis is coming in and out, the plane of the board is a plane of symmetry. Do we have vertical mirror planes? Yeah, we have those too, but you actually don't have to consider that at this point. If you follow the flow chart through, you'll find that we've arrived at our symmetry. And that symmetry is D4H. Okay. So what we're going to look at is the carbon-carbon stretchings and bends and wags and all of that sort of stuff. So let's translate or move, if you will, our molecule over here And we're going to consider, again, these stretching vectors. And so I drew them as vectors in there, the bonds bouncing around. And let's redefine our symmetry elements again. And if you look at the character table for this, do you need to define X, Y, and Z? Strictly, yes, you do. And so we'll do the usual thing where the Z-axis is coming in and out of the board. It's at the very center of the molecule. It's the principal axis of rotation. Let's put the x-axis here and the y-axis here. Along those axes, we actually have some symmetry elements. And again, it depends on what your definition is. But remember, if you have a type of C2 axis that contains atoms versus a type of C2 axis that does not contain atoms, those are different symmetry elements. Okay? And so if we just peruse right quick the character table for D4H, which you can do right now in your book or whatever, take a look at that. Okay? What types of C2s do we have? Well, there's this C2, so we got two C4s. One of those is the counterclockwise, one's the clockwise. We have two C2 primes and two C2 double primes. Okay? These are going to be the ones that will contain atoms in the molecule. These are going to be the ones that don't. And so as a result, the X and Y axes are our C2 primes. There's two of them. They belong to the same class, which means they do the same thing. 2 C2 prime. There's also the C2 axes that don't contain any atoms. And so we draw those on here. And those are our C2 double prime. By default, then, you also see in the character table, there's 2 sigma V and 2 sigma D. Those, again, are different. The sigma V's will always correlate with the C2 prime. The sigma V's are ones that are going to contain atoms in the molecule. So sigma V and sigma V are along our x-axis. One's the xy plane, one's the xz plane, one is the yz plane. And then these guys also define our dihedral planes. Now that's important for when you set up all of your analysis for this. Okay, so let's generate. Bear with me while I write this out. I just copied all of that off the character table. Let's generate our gamma reducible. In this, we're considering the number of unmoved vectors. And so this is a little more rigorous than what we did before. So that my double-headed arrows there, do those move, do those not move? That's the question. And so, see that you'd be glad about that instead of it not being unmoved atoms. All right, so if I do nothing to it, there's 4 vectors. 4 vectors stay where they are. If I rotate this molecule about C4, all of the vectors move. And so this bottom one will end up over, the top one will end up over here, this one will end up here, etc. And so there's a 0 there. Since this C2 is doing the C4 twice, the same type of thing is going to happen. The only difference is the top one here will be at the bottom, and the left will be at the right. Since all of those move, that's 0. Now, observe, this is actually why I pointed out what I pointed out about where you place your C2 primes or C2 double primes. The C2 prime here contains 2 carbon atoms. Right? And the C2 double prime doesn't. So if I rotate about this C2 prime, which is the x-axis, or that C2 prime, which is the y-axis, how many vectors move? The answer to that is all. But if I move over to these C2 double primes, okay, that bisects this vector and that vector. Now we are not considering any type of wave function or anything with this. It's just a vector. What happens if I rotate about either of those C2 double primes? Well, let's take this one, for example. That's horizontal. This vector at the bottom and the vector at the top here will switch places, but these remain, the left and the right ones, remain where they were. So we have a 2 for that character. What about S4? Let's get ahead of ourselves. What about the inversion center? You know what happens with that. Everybody moves. 0. S4 is a rotation about a 4-fold axis and then a reflection. Turns out the S4 axis is collinear with the C4, the Z-axis. It's a manifestation of the symmetry of the molecule. Both the reflection plane and the axis actually exist in this case, but because you're rotating about a 4-fold axis, that's a 0. The plane of the board, the XY plane, is the horizontal. All the vectors are in the plane of the board, or in the XY plane. Consequently, that's a 4 there. They remain put. The sigma v is containing the x or the y axis, right? So that's here, which means all the vectors move. And because the dihedral planes contain C2 double prime over here, if I reflect about this sigma d, the top and bottom vectors will swap places, but the left and right vectors will remain the same. And so that's a 2. And so that's our gamma reducible. However, for the full vibrational analysis, what we must do is generate gamma x, y, z. And where do we get that from? Well, you get this from analyzing the character table for D4H. Now, I'll tell you what it is, and then you can look at that. If you look at A2U in the D4H character table, you'll see that there's an X in set 1. Sorry, there's a Z in set 1. That's one component of this larger representation. X and Y translate as a degenerate pair in EU. So gamma XYZ is the sum of A2U plus EU. And so in order to get this, what I'll do, I'll put this on here so you can see, as I sum all of the characters up for this and this under their respective classes, and that generates gamma XYZ. So, Let's do that. The characters for these, and I'm reading this right off the character table, are 1, 1, 1, minus 1, minus 1, minus 1, minus 1, minus 1, 1, 1. So that's abstracted directly from the character table. For the doubly degenerate situation, we have 2, 0, minus 2, 0, 0, minus 2, 0, 2, 0, 0. And so gamma xyz is the sum of all of these characters, which comes out to be 3, 1, negative 1, negative 1, negative 1, negative 3, negative 1, 1, 1, and 1. So hopefully you can see where I got that from. I found the irreducible representations in the character table that have an x, a y, or a z in set 1. I added the two representations together. That generates gamma x, y, z. And so, once we do that, what do? We generate a thing which we affectionately call gamma total. And it's the product of the two. And so you can see how this might get kind of nasty, kind of hairy, right? If you got characters that weren't 0 in there, but luckily we got a bunch of them. So I'm going to multiply this by this, and that gives me gamma total. 12, 0, 0, 0, minus 2, 0, 0, 4, 0, 2. That's gamma total. What do we do with gamma total? We reduce it. And so now, this next bunch of steps proceeds exactly as we did for the stretch-only analysis. Just you're going to have bigger numbers to deal with. What's the order of this group? One, 3, 4, 6, 8, 9, 11, 12, 14, 16. 16 symmetry elements divided into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 classes. H is the number of individual symmetry elements, the total number of symmetry elements. That's the 1 over H that you're going to use to reduce this. And so we could write all of these out, but since we've done this before, let's just do a couple of them. What's the contribution of A1G? Well, it's totally symmetric. And so the products that you're going to get, if they're all 1s, 1 times 12 times 1 is 12. 2 times minus 2 times 1 is negative 4. 1 times 4 times 1 is positive 4. And 2 times 2 times 1 is 4. And so that contributes 1 time. 12 minus 4 plus 4 plus 4 is 16. 1 over 16 is 1. And so you do the exact same type of analysis that you would find as we did before for the vibration. So I'm not going to write out every single contribution thing like that. I'll just give you the result. And you can do that on your own, and you should find that you get the exact same thing I do if you're following setting up the coordinate system the way that I did it, and you generated gamma x, y, z correctly. Now, the only thing that may look a little bit daunting about this is when you do it, you're going to have a lot more stuff in there, at least at the beginning. But that's okay, because you'll see that it all comes out at the end. So, what is gamma total? Gamma total is A1G plus A2G plus B1G plus B2G plus EG plus A2U plus B1U plus 2 EU. See what I mean? A lot more stuff. A1G, A2G, B1G, B2G, EG, A2U, B1U, 2 EU. 2. And so that is your reduced gamma total. And one of the things you do to check to make sure you do this right, is the sum of the characters under E should equal 12. And so what are those characters under E for this? Well, for all the singly degenerate ones, we have 1, 1, 1, 1, 1, and 1. So where are we at right now? 6. For the doubly degenerate representation, E is 2. And this one as well. However, there are 2 different E ungaratas, 2 different EUs, and so that's 2 times 2. And if you sum that all up, you got 12. So if you do that as a quick check, chances are you're in business and you've got the whole thing the way it should be. Now, if you remember what I said way at the beginning, I'll say it again. This gamma total encompasses vibration, translation, and rotation. We're only concerned with the stretches of the vectors. So, what we got to do is take out now the mess we made and subtract from this gamma xyz and also subtract from it gamma rotational. Now we remember what XYZ was, and that's EU and A2U. What is the rotational component? The rotational one is where you can see the book here, in set 1, you have those R's. So there is a degenerate pair of Rx and Ry for EG. Again, in set 1, I found an R there. And RZ is A2G. Okay, so what I'm going to do is I'm going to subtract those components, those 4 things, from my big thing here. Okay? And if I do that, then what I'm left with is gamma vibrational. And so from this one, I'm going to subtract A2G. I'm going to subtract EG. I'm going to subtract A2U, and I'm going to subtract one of the 2 EUs. Subtract this one, XYZ, the translational part, and the rotational part. So my gamma 5 then is A1G plus B1G plus B2G plus B1U plus EG. plus EU, not EG. Okay. A little less to analyze. How many bands are there? Which are IR and which are Raman active? Now, if you look at this, what we get out at the end, you'll see one of these two types of spectroscopies is a heck of a lot more valuable than the other. And so, if we go and take a look-see at this, the only place in set 1 that I see an X, a Y, or a Z, again, the RX, the RY, and the RZ don't give you this, is the EU. However, in set 2, wherever I see an X, a Y, or a Z, I see that an A1G, B1G, and B2G. And so, what I would see for the stretching, bending, and wagging of this is 1 band in the IR and 3 bands in the round. So that might be the question you're asked on the exam or on homework, okay? How many bands in the IR and how many bands in the round do I see for this molecule with its stretches and its full vibrational analysis? And that's the answer. You see a lot more information in the Raman because you can get a lot more subtle manipulations of low energy things with that. So you can see carbon-carbon bond stretches, which are not high energy. You can see heavy atom bond stretches, like in our compounds, germanium bond stretches, and things like this. There's one more point I want to address without going through a whole nother one of these things. Okay, and let's say, for the heck of it, that we were working with a molecule that did have D4H symmetry. Okay. And in that, we found that we reduced a gamma vibrational, and it gave us a 1G plus 2 A2U plus EU. How many bands would that represent? Well, if we look in set 1, A1G is not IR active. There's nothing there. A2U has a Z in set 1, so that is IR active. And EU is the degenerate X and Y, and that's IR active. In the Raman, A1G is Raman active, but the other two aren't. So how many bands does this translate to? Right? So you did all your work, you come down to here, you're getting ready to answer the question. It's got this many IR bands, it's got this many Raman bands. There's only one Raman band, but there are 3 IR. Because even though you have 2 stretches, or wags, or bends, or whatever they are, of the same symmetry, they're going to probably have different energies. It doesn't matter if they do or don't. You have 2 IR bands coming out of this, but only 1 out of the EU. And so the take-home message there is if you get a coefficient in front of one of these, that gives you that coefficient of bands. But doubly degenerate E type things, or triply degenerate T type things, do not give you 2 or 3 bands, respectively. It's just one. And so that is the second lecture on this, and that is all we really need to know about how to use this for vibrational spectroscopy.